All right, welcome everybody. This is the fifth installment of this year's Western Lake Erie Basin Advisory Group's 2026 Winter Webinar Series. We're having these webinar series every winter to provide our community with information about managing the environment to reduce nutrient pollution in Michigan's portion of the Western Lake Erie Basin. This winter series will continue for a few more weeks until April 7th on alternating Tuesdays and Thursdays at noon. And you can find the full schedule here on the link that I'm about to put in the chat. And you can also access past recordings from the previous webinars that we've already had this year. So my name is Allison Bressler, if you don't know me yet, and I'm the program manager for the Western Lake Erie Basin Advisory Group. This community group works collaboratively with Michigan's quality of life agencies, so MDARD, EGLE, and DNR, to inform how the state implements projects aimed at managing and monitoring phosphorus to improve water quality in Lake Erie. The WLEB Advisory Group and this webinar series are generously funded by a grant from the Herb Family Foundation. So in today's webinar, we welcome two speakers. First, we have Jeremiah Asher speaking. He's the Assistant Director at Michigan State University's Institute of Water Research, and Dr. Bruno Basso, who is a professor at Michigan State University. So Jeremiah's research focuses on translating field research to decision support application systems. His chief application developer, he is the chief application developer for two nationally awarded decision tools, the North Carolina Ecosystem Enhancement Program and the Water Withdrawal Assessment Tool Interface for the state of Michigan. Jeremiah leads the IWR portion of this project that you'll hear about today. He's overseeing project tasks, ensuring QA/QC for sampling and data activities, and coordinating with project partner teams. Our second speaker today is going to be Dr. Basso. His research integrates the fields of biophysics, climatology, hydrology, genetics, agronomy, and soil science to understand the overall agricultural systems and to improve decision-making across a broad spectrum of stakeholders, from small farmers in the developing world to industrial producers and policymakers at all scales. Dr. Basso approaches this work by developing and applying advanced crop system models to predict the impact of weather, soil, and management on short-term and long-term yield, nutrient uptake, water use efficiency, and environmental outcomes. And you'll hear more about one of those today. Thank you for joining again. We're going to have these two presentations, and then we will have a Q&A session at the end. So as you think of your questions, please just pop them in the chat, and then I'll read them out at the end, or we'll have someone address them in the chat before it's over. And then we'll also have an opportunity for you to unmute and ask a question at the end. So Jeremiah, I'm going to pass this off to you to start your presentation.
Great. Thank you, Allison. And thanks everyone for joining this afternoon to learn a little bit more about the performance-based conservation adoption program for the Western Lake Erie Basin and my digital farms that Dr. Basso will be talking about. Today, I'll be providing a short overview of the performance-based conservation adoption program. I'll share some updates since our December webinar that we also did with Allison, where we went into more detail about this program and why we're using performance-based approach instead of just paying for conservation practices directly. We'll take a sneak peek at some of the Pay for Performance platform pages and talk briefly about how they integrate with My Digital Farm. And then Dr. Basso will dive into the yield stability and profitability mapping in greater detail using My Digital Farms. So this program was funded by the Michigan Department of Ag and Rural Development. It is led by the Institute of Water Research at Michigan State University, and we have funded partners with the Alliance of the Great Lakes, MSU Center for Regen Ag, and MSU Extension as well. The project was $12 million in total for the budget. Of that, $7 million is going toward conservation payments to producers. We have about $1 million that is going toward incentive payments for what we're calling technical assistance providers that will help to enroll the producers into the program. And about 4 million went into the development, management, and implementation of the program over a 7-year period. So this is just a brief timeline of what that project, the course of the project looks like. So in June of 2025, we had a kickoff meeting that was done at the State of the Lake Erie Conference for Michigan. We went into July and started doing our project planning and development. We have an advisory team made up of multiple stakeholders that helps to provide input and guidance on various aspects of the project as we go into in through the development. In September, we moved into model development where we developed a SWAT model. That's a soil and water assessment tool, and we developed that for the entire Western Lake Erie Basin on the Michigan portion. And then in November, toward winter, we started moving into designing the interface, and that's kind of where we are now with working on some of those pages. And then anticipate enrolling producers later this summer, and then the implementation and rollout of that program will happen from 2026 all the way to 2032, where we'll wrap up in September of 2032. So, we start to ask about, what is pay for performance, or we talk about, performance-based conservation. And what we mean by that in this program is instead of paying specifically for a conservation practice, we're really looking at paying for the outcome. And in our case, that would be phosphorus reduction that occurs from that particular conservation practice on the landscape. So to give an example that if we look at putting, say, cover crop as a practice on a field, we would take that practice, we would do an analysis using a model to estimate the performance of that conservation practice. So in our case, I mentioned SWAT. SWAT looks at a number of different parameters, including the soil types, the slopes, precipitation in the area, the management of those fields, and grows out the crops on a daily time step. And then as it does that, we're able to project, in our case, we're looking at phosphorus, what the phosphorus reduction would be for that particular field. So let's say in this case, it was 40 pounds of phosphorus reduction. And if we pay $125 per pound of phosphorus, which is kind of what we've been working on with our advisory team and internal team, and I think is where we'll probably end up landing for our payment rate, then the producer would get $125 times that 40 pounds of phosphorus reduction. And in different fields, in different locations, different practices might perform different and might have different payments because, again, we're not paying for a particular practice, but we're paying for the outcome or the performance of that practice. So in year one, the conservation practices that the program will be offering will be cover crops, riparian buffers, filter strips, crop rotation, low productivity land reserve, and this is essentially kind of looking at what Dr. Basso would be talking about, where if we have areas of low productivity in the field, we might be able to pull those out of production and put those into a buffer or prairie strips or some other sort of vegetation. Also, drainage water management, no-till or reduced till with subsurface application or cover crops. And then our subsurface fertilizer placement in combination with nutrient management or the no-till, reduced till. We do have additional practices that we'll be looking at for year two. This would be prescribed grazing and agricultural runoff treatment systems. We were hoping to get grass waterways in year one, and it still may happen, but we have a few things that we're working on with the model outputs for the grass waterways. So they may or may not happen in the year one, but we do anticipate if they're not in year one, that they'll be in year two. All right, I want to talk a little bit about the process for how somebody moves through the pay for performance system. Everything that we're doing starts with what we're calling the technical assistance provider. That technical assistance provider is going to be the person working with the producer and enrolling them into the program. We have a series of tools that we'd like to offer the technical assistance providers to help have conversations with producers about different ways to get conservation, into their farm or the management of their fields. One of those is ACPF, which looks at various risks on the landscape, for runoff and looks for opportunities to put in, say, grass waterways or filter strips. MDARD is supporting a lot of the work that's happening in the Western Lake Erie Basin with ACPF. We also have another tool that we're offering called Sensitive Areas Identification System that was developed at the Institute of Water Research at MSU and funded by NRCS. What that tool does is looks at sensitive areas on a field or a farm and then provides recommended best management practices to address those. And then My Digital Farms, which we'll talk a little bit more about today, looks at low, yield stability within the farm or low yields, and looks at the profitability of those fields and looks to see if there's opportunities to take those out of production and put those into a conservation practice to make that field more profitable. And I'll zoom a little bit closer in here just to give a little bit of an example of what these tools might look like. So for Sensitive Areas Identification System, I just digitized this field behind the house that I grew up in Monroe County. I clicked Generate a Report, and within a few seconds, it generates a report of this particular field and identifies risks at that location for phosphorus runoff, concentrated flow, wind erosion, and then lists the different conservation practices that could be used to address some of those risks that were identified at the farm. It also then provides a contact information for a local service center, and then provides a series of supportive maps for that field. So it'll show aerial maps, it'll look at soil maps, also provides a topographic view map here. It generates concentrated flow lines across that field where runoff might concentrate and run across. And then it also looks at wind erosion sensitivity, which I can identify that those locations are pretty accurate for wind erosion there. And then provides a list of the practice definitions for those particular practices that were recommended. So if the technical assistance provider then uses one of those tools, they might be having a conversation with the producer, identify a risk area, and maybe say that they want to put in conservation or cover crops at that location. They can either import the field boundaries directly in and do an analysis, or they can digitize a field boundary if they'd like. Once it does an analysis, it'll show, in this case, say 40 acres of cover crops, has a reduction of 20 pounds of phosphorus with a payment of $125 per pound of phosphorus. That user might be able, or that producer might be able to get $2,500. They can decide if they want to do that or not. And if they do, they can enroll in the program, develop a contract, and then go ahead and put in whatever that conservation practice is. Once that conservation practice goes in, there'll be a verification that the producer will do. That likely will just be taking a picture, with that practice with a specific time. It might be including seed tags or bin runs. And then taking that information and using a mobile-based app that we have that they can take a picture, it'll timestamp and geolocate the information, and then that'll get sent over to someone at MSU who will review that verification or verify that that practice has gone in right with appropriate documentation. And then the Lenawee Conservation District will release payments once that practice has been verified to the producer. And then at the end of that process, any of the nutrient reduction benefits will go into the nutrient tracking dashboard that's been built for the state to help track phosphorus reduction into the Western Lake Erie Basin. All right, I'll switch gears for a minute and give you a sneak peek at a few of the pages that are being developed on the Performance-Based Conservation Adoption Program platform. This will be the landing page for coming into the system, and at the top, users can access functional parts of the platform like the resources for technical assistance providers, running a field scale analysis, or checking contract status. If we move over into the main area of the page, users can get information and overview about the program and see any recent updates that are happening. And then here up in the kind of the middle, they can check out the Get Started or learn more information. So if we go into the Get Started section, it opens up a Get Started page, which provides introductory video about the program and then funnels users into kind of two distinct areas for the site, those for technical assistance providers and those and producers. So each of these areas focuses on tools and resources needed for each of the types of users. At the beginning process, the producers are really directed to get in contact with a technical assistance provider if they're not already working with one. And so a lot of the functions and features initially are geared toward the technical assistance provider until that producer enrolls in the system. And then once they've enrolled into the system, then there's opportunities for them to do their verification, work through their contracts, and check out where their payments are and what that process looks like. All right, if we go to the technical assistance resources page, this is where a lot of the resources will be available to technical assistance providers. They can review the contract standards. They can view and interact with various maps and evaluate, in this section for maps, they can evaluate producers' fields. They can also go in and access some tools like the ACPF, Sensitive Areas Identification System, and the Michigan or the My Digital Farm that I mentioned earlier. And then they can also go in and manage their clients or customers all with the platform. Just to show an example here, if we go into the practice definitions, here the technical assistance providers can see the latest practices offered through the program and rely on or relay that eligibility requirements and other information to the producers. Producers will also have access to the practice definitions and eligibility as well, so they can look through that on their own. If we click into the tools, this is where the taps can view access to the three tools that I described earlier for exploring the potential risks on a farm and looking for opportunities to add conservation practices where needed. So if we go into that, these are the three supplemental tools, again, offered through the Performance-Based Conservation Adoption Program. Today, we'll be spending a little bit more time with the My Digital Farms. And this is using the My Digital Farms is really a great way we see for working closely with producers to explore new opportunities for improving their profitability and increasing conservation all at the same time. And so before I hand it over to Bruno to talk about My Digital Farms, I'll just mention that we plan on providing an online and in-person training on the Performance-Based Conservation Program this summer. And if you're interested in learning more about that, you can contact myself or David DeYoung with the email addresses up here. If you're not able to capture those, you can also contact Allison and she can get you in touch with us. And with that, I'd just like to thank you again, and I'll hand it over to Bruno.
Thank you, Jeremiah. Hi, everyone. Pleasure to be here and share some of the latest work that we've been doing, as mentioned, on the digitalization of farms across the US, as you will see, and the great promises that I think they offer, especially in this really ambitious and fantastic project. So I need to provide a little bit of background, and so without going necessarily much away of the concept of the My Digital Farm, I really wanted to you probably know this, that we've been bombarded by this, technologies present on farms, and the point of these slides is really to show the opportunity that we have in implementing things, going from high, precision application of both fertilizer. That's one of the drones of the farmers' fields, understanding spatial and temporal variation and the drivers of that variation, opportunity for calculating carbon intensity score for whether it's biofuel or sustainable sourcing, and through advancement in robotics, that robot there applies water differently for every row, and my picture in the middle just to show there that there is so much more attention now to agriculture thanks to this big jump that we've been doing with digitalization, that even magazines like Forbes, would now allocate, editorials in the context of digital agriculture. The machines have gone through a serious revolution over the last 30 years or so when we started having GPS mounted on board. And now you can really have incredibly precise management on the way seeds are placed, the number of seeds, precision application of fertilizers, and so on. So basically, the train of technologies in robotics and automation has left a long time ago. It's becoming default, and we still need to capitalize significantly more, as you will see. So one of the main, I think, revolution that happened in terms of data collection is the opportunity to collect yield information. And you all, whether you're a farmer or you've been exposed, now we have a knowledge of spatial variation through yield mapping, yield monitor technologies with sensors mounted on the tractors, whether they are, the force or the beams, and different level of sensors, high precision. You still have to clean the data, but the map that flips there is really what's I want to point the attention to. That's a field in Iowa, has many of few hundred acres, that basically has a significant spatial and temporal variation. So the spatial patterns are not always the same. Both annually, spatial patterns vary from one year to the next and from one point to the next. So both fields, the one in Michigan, they're a little bit more rolling terrain, highly dependent on the interaction between weather, genetics, and soils and management. So if we develop this concept that you look at, spatial and temporal variation in a continuum sets of analysis, where you analyze how different a pixel is from the neighbor and how it varies over time. So the really complex spatial and temporal variation that you see could be converted into what we call this yield stability, which are areas that they constantly perform, as you see the areas here in blue, constantly high yielding or medium or low. So stable means in terms that remains within that category. It doesn't go beyond one standard deviation. So the variation, even though occurs between years, is still limited. And then you have the truly unstable zones, are the ones that need to be paid attention during the season, because they can be high one year and low another year. So this yield stability concept has been fundamental in understanding spatial and temporal variation and be able to drive management decision, as you will see, even though in a summarized version. And now we've been able to do this sorts of analysis, first inheriting a very large amount of yield mapping, yield maps from farmers, but then several years ago, I developed this algorithm that uses remotely sensed image in a novel way, that basically before the signal saturates, evaluates the level of changes, as I just mentioned, how spatially variable the pixels are and how they vary over space. And so now you can basically click on any of these fields and you have a knowledge of spatial and temporal variation of these areas, that they're constantly high yielding, medium or low or unstable. That's an example of any field in Michigan. You'll see even a little bit more in details how we plan to make these maps available. So the question would be, Okay, well, yield mapping is the ultimate truth, high quality. The images have a level of uncertainties. As you know, the reflectance is still a model type of approach of the reflectance above the atmosphere, and it gets converted into what the different bands and reflection means. And so we've done a terrific job over the years in converting, true vegetation indices. And so here is a comparison of the spatial pattern. And for some fields, depending on the size and the type of management and the rotation, you may have an overview of between accuracy between, on the worst case, 50 or over 80%. But you can see visually whether you use Planet, which is at 3 meters, it really captures the spatial pattern without even being in this field, obviously, over the last 10 years. Sentinel, as well as at 10 meters, freely available, and that's what my digital farm is now based on, even though we have access to Planet. And then Landsat at 30-meter resolution. So this is important to realize how we're doing a good job in capturing spatial pattern, and most of the time we certainly are. The other concept that evolves from yield stability map is this profit stability map. You can have yield maps from any field in this case, and you convert into, we know exactly the cost of production. Farmers would tend to not always know all the details, but they certainly know how much it costs to produce, a bushel of corn. And so just 1 year will give you a certain level of map. But if you start using the way we show this map now with unstable zones with the mesh net, which means that the predominant areas of the instability is mostly, as you can see here in the green, is mostly medium, but it could flip. It could go to high or low. And when you do this cumulative analysis, and so that's what we call profit stability, these red areas, that means out of these 7 years of corn, they constantly lost $200 per acre. And that's really what drove the attention when we start bringing this technology, in front of farmers. That a common comment was, I wasn't ready to see this. Unfortunately, this is predominant because low and stable zones, the one that constantly underperforming, on average lose between $200 and $300 per acre, because they're not necessarily not producing. But if you produce 120, 130 bushel corn on those low productivity areas, the break even is still close to 175 bushels. So you're really far off from breaking even. And so this concept really expands in what we call precision conservation, where you take the profitability map, as you will see, in deciding, is there an opportunity to vary nitrogen as we do? I have a really an outstanding group of people working in my lab in close connection with people in the extension, and especially Rich Price that works in both context, and takes the information that comes out of the lab and presents it in farmers. So we've been able to get a significant amount of traction in converting through precision, basically prescription maps implemented through a project of NRCS. So what you see here was truly implemented. We have about 30,000 acres in Michigan that they've been either applying variable rate and returning the as applied in response to the prescription that we gave them, or they have converted and they got paid to remove these low productivity areas into pollinators, or any type of vegetation that wouldn't be corn and would require the heavy duty type of chemistry and cost associated with it. And so in the end, you can really, which is the goal of this project, you want to optimize economics first while optimizing resources. And so paradoxically, you can make money off of selling ecosystem services because of the performance, as Jeremiah just mentioned, but while maintaining productivity in the areas where at least there is a response, and not in areas where there is no response. So one of the core technology, in addition to the yield stability map, is modeling. And so I developed these crop simulation models, a SALUS process-based model with a high level of knowledge about genetics, so you can simulate whether you have a type of BT crops and different rooting depth, or new cultivar versus cultivar, and be able to model response to nitrogen, to phosphorus, and So that's used to basically delivering the rates as we did for nitrogen. And this is just an example to show, based on the stability map, it didn't matter if you kept adding nitrogen or low productivity area. It does not work that way. Low productivity areas gets less and less, not more, because if over time you have seen that these areas do not respond to the similar management that a good zones get, you just cannot keep doing the same mistake, hoping that these low productivity areas will ever get better. And in fact, this is the response, whether you go up to close to 250 pound or 100 pound, you get the same level of yields, as well as the level of economics changes drastically. And opposite end, in the high yielding zones, you can even push the envelope and be able to get, greater yields, because you have deeper soils and greater water availability that will respond to the increase of the inputs. So in addition to the prescription, we send these biodiversity conservation areas, which we really hope that will be successful within this project, because you really it's a game changer in terms of profitability as well as environmental sustainability. And so these are the maps that have been converted and farmers implement. That's the way, an example of how they are implemented at a field scale. This is a video taken by Rich to be able to see how this is all implemented. And the farmers, after the 5 years of this project that we had, have remained in the precision conservation approach, because obviously it brought significantly more economic as well as benefits by even increasing yields to the neighbor's land next within the same field. I mean, the area next to the BCAs. This was covered just to be able to tell you how much the journalism still is interested in this type of things and fact checking, and they came and they wanted to see all the precision conservation areas and the reduction, and we quantified the greenhouse gas emissions that were reduced, the lower nitrate leaching, and the greater economics that farmers. So if you're interested in learning more, the farmers, the article describes this in details. So coming to the core of My Digital Farm, I've summarized, instead of having screenshot, I synthesized this in a video, and specifically for the West Lake Erie Basin. And the system is not launched yet. It will be available in the next a month or so, and you will obviously know ahead of time. And I will explain while I talk. There's supposed to be music. I don't know if you hear, but you can still hear me. And so you basically have a digitalization to the extreme. You go to the site and you have My Digital Farm. It will get you to a page where all the fields are visualized, and that's where all the fields that have been monitored through remote sensing and yield stability maps. So they're all available in partition the way I described it, the constantly low yielding. That's what's really key, be able to see which area it loses or gains. So this is for the West Lake. If you click on the field, you'll be able to know how much money you're making or you're losing. You can type an address, or you can basically get to a field that is already, these are boundaries that we have created beyond the NAFs. So there is a very high level of precision even in the boundary fields. And these are the areas that need attention, whether it's a reduction of fertilizer or a complete removal. The important thing is that you have a cumulative stability as well, a profit stability, and an understanding of which year basically there is a performance that varies. So you will see the areas that they constantly give you a return, and the one that fluctuate, or the one that constantly make you lose money. And so that's an example of another field. The first version of the program will have basically these available, and the second version, which is here as a prototype, will also allow you to basically potentially run Salus and be able to get a sensitivity if you want to understand if you change a tillage. And if you're interested in beyond phosphorus, maybe building soil carbon and all the co-benefits associated to conservation practices that you could adopt and be rewarded from them. So here you run the value here, you can change the type of years that you run, but then you'll have, the visuals of how much has changed between one treatment and another. And you could also be, if it deals with profitability, you can go back and decide that if the cost was different, that the normal and yours was particularly cheaper or more, you can change the cost of the sales and be able to reshape, the profitability map. So very promising tools, fully useful and potentially closely connected to what we're trying to do here, because conservation is one of the aspects. So I'm going to stop here. If I have an extra minute, I want to assert that we have opportunity. We haven't delivered prescription maps of phosphorus, but we could. We've been working closely both on modeling and just to be aware, we've done a significant amount of study. We have knowledge of phosphorus application and soil organic matters. And I mean, there's a huge database of about 1,700 farmers representing close to 1 million acres of corn in general as a farm. And here is the application of how much phosphorus was applied, and manure, whether they do it or not, the types, the formulations, and anyway. So this is just a quick shot of the lab. Thanks again for the opportunity to share this with you.